Welcome back, dear students of class 12. So today we'll be continuing with optical isomerism. So in our previous video, we had discussed about stereoisomerism and its type. In that, we discussed about geometrical isomerism. So today we'll be discussing about optical isomerism. So the name itself suggests optical, optics. It is related with light. Okay. So there are certain compounds. Which rotates the plane of polarized light either towards right hand side or towards left hand side. Such compounds are known as what? Optical isomers. They are known as what? Optical isomers, and the phenomenon shown by them is known as optical isomerism. So these four compounds, to show optical isomerism, they have to be related to each other by mirror object and mirror image. Okay? And they have to be non-superimposable. So let's take an example. Suppose you have a letter, say H. So suppose here you have a mirror, and in mirror, how will this H look like? It will be at the same distance as the object is from the mirror, at the same distance, and this side. Suppose this is 1, 2, this is 3, and this is 4. This 1 and 2, since it is nearest to the mirror, this side 1 and 2 will be on this side. Okay, nearest to the mirror, and accordingly you will be having this image. So, in a way, if I remove this numbering, then what can we say is we get the same exact image. Now this H, suppose this H, you are not doing anything, you took it out and you are placing it over this object, that is your H itself. So what will happen? All the parts, 1, 2, 3, 4 parts will exactly match with these 4 parts. So what we are doing, we are just taking it out, we are not bending it or tilting it, we are taking it out and putting it over it. So we get what? These sides, these 4 sides will exactly overlap with this edge. Now such mirror image is known as what? Superimposable mirror image. Please, this term is very, very important. Now this is superimposable, the image of this edge is superimposable on its object. Now, here it's known as what? Superimposable. Please remember this. Now, such mirror and object, these relations, now they will not be showing optical isomerism. This part is very important. If the image and the object, they are superimposable, then they will not be showing optical isomerism. So, for optical isomerism, what has to be the relation between the image and the object? They have to be non-superimposable. So, the first condition is non-superimposable. For example, suppose you have, say, B. Now, this letter B, how will it look like in the image, in the mirror? How will it look like? Now this part, since it is nearest, it will be looking like this. Yes or no? Now this B, this is the image of this B. This side is the nearest, therefore you will be getting this image. So now if you pick it up and try to place over it, then what will happen? It will be like this. So you will be having this image. You are not tilting it, you are just picking it up, putting over it. Is it superimposable? No, it is not superimposable. Now, such mirror image and this object, now they have the tendency to show optical isomerism. Hope this is clear. This was explained in class 11 also, in organic section. Okay? Now let's come to optical isomerism, and here we are discussing about coordination complexes. So, you know, about coordination complexes. They can have 4 ligands, coordination number 4, as we discussed in the last video, and it can also have coordination number 6, which is known as what? Octahedral complexes. Now let's discuss about coordination number 4. Now those complexes of the type ML4. Now this is the type of complex which has coordination number 4. Okay. Now they can show 2 types of geometry. One is tetrahedral. The other one is square planar. Okay. So with coordination number 4, 2 types of geometry is possible. One is tetrahedral, the other one is square planar. Now here, if you have a complex of the type, say M, A, B, C, D, this is the complex. Then here, tetrahedral complexes of the type M, A, B, C, D. Here A, B, C, D are what? Ligands, different ligands. Now, they do not show optical isomerism because these complexes are very labile. Please remember this term. Labile means from one form to the other form, it interchanges very quickly. Because of that, we will not be able to isolate the 2 different forms, that is D form or the L form. Therefore, practically tetrahedral complexes, coordination complexes do not show optical isomerism. Now, square planar complexes. Now, this is square planar complexes. Now, here let me tell you one more point which is very important. If a complex has plane of symmetry, okay, what? Plane of symmetry, then they will not be showing optical isomerism. The square planar complexes, they are optically inactive. They are optically inactive because they have plane of symmetry. Plane of symmetry. Now those complexes which have plane of symmetry, they will not be showing what? Optical isomerism. So both tetrahedral complexes as well as square planar complexes, they are optically inactive. Please remember this part. Now, if you want to this part, they have a plane of symmetry. Remember class 11? We have discussed about tartaric acid, and it had what? Plane of symmetry. Therefore, it was meso-tartaric acid was what? Was optically inactive. So you can refer to your class 11 those isomerism part also. Now, let's move on to complexes which has coordination number 6. Now we will be discussing about complexes which has coordination number 6. Now they will be of the type ML6. As I have told you before also, here 6 doesn't mean hexa, it is octahedral complexes. Please, they are known as what? Octahedral complexes. Now, these octahedral complexes, okay, they show optical isomerism if these ligands, one of the ligands is what? If they have di-dentate ligand. So, this optical isomerism is possible in compounds having coordination number 6, that is octahedral complexes, if they have what? Di-dentate ligand. So common in coordination number complexes with coordination number 6 with di-dentate ligands. So now let's discuss about this types of isomerism. Okay, now let me tell you once again. You have learned about cis isomer and trans isomer in geometrical isomerism. Now the trans isomer, they will not be showing optical isomerism. Please remember why? Because they have the plane of symmetry. So if they have the plane of symmetry, then they will not be showing optical isomerism. So it is only the cis form. It is only the cis form which shows optical isomerism. So let's discuss about different types of optical isomerism. So the first type that we have is NAA whole to X2 type. So here we have example of cobalt complexes, that is CO, Cl2, En whole 2. So this complex will show what? Will show optical isomerism. And let me tell you once again, it is the cis form only, not the trans form. So let me draw the structure of cis form then. First let me draw the structure of trans form. So cobalt we have, and here we have 4 ligands at 4 corners, one above the plane, other one below the plane. Now in this complex, what we have is, we have En. En means ethylene diamine. En. And here what we have? We have Cl. One Cl above the plane, another one below the plane. Now this is the trans form. Now it has plane of symmetry here. Now see, if you pass a plane exactly through this Cl and this Cl, then what will happen? It divides this molecule into exactly 2 equal halves. Therefore, this is the trans form. Because of this reason, they are what? Optically inactive. Optically inactive. Okay? Now let's discuss about the cis form. In the cis form, what we have is, the formula is same. Here there is differences in the positions of these groups. Okay? Now here in cis form we have ethylene diamine between this and this, and here En is present. Ethylene diamine is present here, and Cl and Cl are present at the adjacent sides. So if they are present adjacent to each other, then they are known as what? Cis form. Now this cis form, if you draw its mirror image, you are drawing what? You are drawing mirror image. Then how will it look like in the mirror? You have this complex, and 4 corners, you have 4 different ligands, one above the plane, the other one below the plane. So En is nearer to this mirror, so this En will be present here. The other En, this is En, ethylene diamine, okay? And Cl over here and Cl over here. Now these two are what? 2 mirror, this is the mirror image of this object. So if you pick it up, put it over it, are they superimposable? No, because this part will be coming towards this side. Therefore, it is not superimposable. Therefore, now they are what? Optically active. The one that will rotate the plane of polarized light towards the right hand side. Towards the right hand side, that is the dextro-rotatory form. This is the D form. And if it rotates the plane of the polarized light towards the left hand side, then that is the L form. So these two are optical isomers of each other. Okay, this is one of the examples. Let's discuss about more examples. Now the other example that we have is of the type MAAX2Y2. X2Y2. Okay, this is the other type of this complex which shows optical isomerism. And the example is cobalt dichloride, 2Cl, 2NH3 groups, and En. So this complex, okay, this complex will show optical isomerism. Now let me draw the cis form of this one. Okay, so here what we have is cobalt is present at the center, and one of the ligand is present above the plane, the other one below the plane. And here what we have is, in the cis form, you have these like groups nearer to each other. They are very adjacent to each other. Cl, NH3. Then what is left? En is left. So this En, that is ethylene diamine, will occupy these two positions. Now if you want to have the mirror image of this one, you can now easily draw it. So here what is present? NH3. So it is nearest to the mirror. This NH3 will be present here. The other NH3 here. Cl, and since this En is farthest from the mirror, here also En will be farthest from the mirror. Now these two complexes are mirror images of each other. They have mirror image relationship, but they are not superimposable. Pick this molecule up, put over it, En is present this side. Here, if you put this over it, En will be coming this side. Yes or not? So they are not superimposable and they are optically active. Please remember this. And this is the D form, dextro-rotatory form, and this is the L form. Okay? So what you have to remember? You have to remember the type, okay? And you have to remember the examples. See, these examples, they'll ask you what type of isomerism is shown, and they'll ask you to write the isomers of this molecular formula. Therefore, you need to draw its mirror images, and so they are optically active. Now let's discuss the third type of optical isomerism in octahedral complexes. Here, the type and example is different. Now, those complexes, okay, these complexes will be of the type M, A, B, O trans type, and example is cobalt, En, O trans. This three, and since the positive cobalt is positively charged and its oxidation is 3 plus, therefore here you will be having 3 plus. Now in this case, as you know, the central metal ion is always present at the center, at the corners, the ligands above the plane, and below the plane also you have ligand. Now in this case, this En group, ethylene diamine, how many of them are there? 3 En groups are present. Therefore, these 3 En groups will occupy these positions. En, and here En will be present. Now these 2 positions are unoccupied. Therefore, the other En group will come here and occupy the other 2 remaining positions of the octahedral ligand. Now, if you draw its mirror image, then you will be having this En group. This is ethylene diamine. Please don't forget. And this En is nearest to the mirror. Therefore, this En will be present here, and this En, ethylene diamine, will be present over here. So these 2 are what? Mirror images. Try overlapping them. Then they are not. You can see that this En is present this side, so it will be present here. That means it won't be superimposable. Okay. Now, if they are not superimposable, then they show what? Optical isomerism. These two are the optical isomers of this molecular formula, and this is the D form, and this is the L form. D form dextrorotatory, as I told you, which rotates the plane of polarized light towards the right hand side. Okay, right hand side. And this L form means what? Left. So you can remember this way also. L stands for left. So they are going to rotate the plane of polarized light towards the left hand side. So under optical isomerism, this was for today's discussion. Now in the next video, we will be discussing about valence bond theory. So till then, please keep on practicing. This looks complex. The topic itself is complex. It looks complex, but if you practice it, if you understand the basics, it is very, very easy. You just need to practice it. Take care. Thank you.